Are we ready? Are we waiting for anyone? Okay. Welcome to the first session. My name is Mike Stay. I'm the CTO of Pyrofex. This talk's going to be about RChain namespaces and regions and how all that stuff works. A validator is a participant in the Casper protocol. So Casper requires each validator to know what the entire set of validators is. This is something that that we argued a while about. We have another notion of grouping together validator sets that's orthogonal to what we'll talk about here, that allows us to combine different blockchains and some other stuff, but that's outside the scope of this talk. So in this talk, validators, participant, everybody knows about everybody else. Let V be the set of validators. So then we have a non-empty finite set R of regions. So we may have 10 regions, may have 100. That number hasn't been decided yet. But then this function, little v, assigns to each region some non-empty set of validators. So that's the positive power set there. We say a validator inhabits region X if V is in V of X. Regions get to set slashing criteria on the validators that inhabit them. So essentially performance criteria. They have to be up to the job of doing the validation, otherwise they get kicked out. Oh, they may also get kicked out for equivocation. The set S of namespaces is the, sorry, not positive power set, is just the plain old power set. Plain old power set of the set of regions. So the validators for the namespace S join T are the ones in S unioned with the ones in T. Now, the reason I made that change from positive power set to power set is because we also want to include the bottom element, that is the join of no regions. What that means for the namespace is that there will be no validators in that set, and that will become useful later on. Deploying code in a namespace with many joins will be more expensive since more validators have to validate the messages. The execution of this can be slower or otherwise constrained since the criteria for inclusion of a validator may be less strict. You may have one region where you need really high performance things, and then you may have another region with much lower stake serving some local neighborhood. And so once you'd have to do a join, then the ones in the high performance one have to be more forgiving of the ones in the local neighborhood namespace. All names in a namespace are quoted processes. So if P is a process, then quote P is a name. We also say at P. Names created with new have this special form. There's this construction private, which means that you can't see this information from within the program. This is an unforgeable thing. This word private doesn't exist in the grammar of contracts that people write. It's only used internally to keep track of this stuff. So the UID makes it a unique name, and it also keeps track of which namespace it comes from. Ground terms live in the namespace bottom. So you can send on a name like hello, just the string. You can send on the name one. But when you do that, it shows up on the blockchain as having been sent, but immediately gets thrown away. So it's useful for debugging and for doing other similar sorts of things. It also means that we don't have to worry quite as much about processes that we would like to confine communicating with each other over these ambiently available names. So it's closer to an object capabilities discipline this way. Quoted outputs live in the namespace of the name being sent on. So here we're sending the process Q on the name X. So the namespace of the quoted process is the same as that of X. Similarly, quoted inputs live in the join of the namespaces, here for Y and there for Q. namespaces. A par, if we have P par Q, and then we take the name of that, it's the namespace of P join namespace of that Q. So that allows us to do this neat Diffie-Hellman-like construction. So if we have two processes, and each of them exchange names, A and B, they send to each other, then they can construct a new name that is star A par star B, and you take the name of that, in the namespace A join B that they both share. And if A and B are created using new, then no other process can possibly send or listen on that name. So it's a secure channel for the two of them to communicate on, no matter what their original namespace was. If little x is in the namespace X, then both of these processes run on the validators of X. So this is different than the name you get from quoting X bang Q. This is where the code X bang Q runs. So if I'm running some code and I get to a point where I'm sending on a name that I've received, that chunk of code, when my namespace has reached finalization, or at least that my node has become satisfied that that send cannot be revoked, then it sends that chunk of code, removes it from its own state and puts it into the namespace, the state of the namespace elsewhere, and then it will run there. And once my namespace is satisfied that that one can't roll back my deployment of that code over to that namespace, then I can continue forward. Otherwise, I have to continue trying to put it into that namespace.
Could you repeat that?
Yeah, so let me draw it over here. So we've got, say, for y from z, and then here we do y bang q. In parallel with this, we say z bang star x. So here, this send on z and this receive on z synchronize, and this evolves to x bang q. Now, if all of this was happening in the namespace z, because we're listening on z here and sending on z here, this should not be running in the namespace z. X is a name from big X. So this namespace and the namespace X usually are operating independently of each other. What we want to do is move this code over to there to run. In order to do that, Z has to be, or X has to be sure that Z can't roll back its choice to send this. So once X is satisfied that Z can't roll that back, X can add this to its state. Then Z has to be sure that X can't roll that decision back. So once it gets to a state where Z is satisfied that this can't be rolled back, Z removes this from its state. Now this has moved over there. And we'll have another slide on it later, and the next presentation will go into that in some more detail. But we can discuss this in our breakout sessions more if you'd like to. Joins between names that are not in the same namespace is a type error. So if we have over here for A from little x, B from little z, do some process P, this is not allowed because little x lives in big X namespace and little z lives in big Z namespace, and they're largely independent of each other. We don't have a notion of a join block between namespaces. This is the only way that two distinct namespaces interact. Bundling. You can't pattern match on the interior of a bundled process. So we have this notion of pattern matching on processes that's used for all kinds of things where if we didn't have bundle here, we could match on a par, and it would, with a little bit extra than what we've got now in the interpreter. If you can say that I want two pieces, neither of which are nil, then we could split that apart into the P part and the Q part. But with a bundle around it, this becomes sort of opaque, that all you can do is grab the whole thing. You can't take it apart into its constituent pieces. That's important because if you have an unforgeable name inside a piece of code, but you would like to give that code to some other process to execute and interact with, then you don't want them to be able to take it apart and pull out that unforgeable name that you'd like to keep secret. That's important for the sealer and unsealer patterns. Processes, all processes, maintain 2 bits for whether you can send or receive on the corresponding name. So if I've got P, there are 2 bits for send and receive. At P, you can listen on if the read bit is set, and you can write on if the write bit is set. You can send on if the write bit is set. Bundling lets you mask off bits. So if P has both read and write, this gets the write-only version of the process. This gets the read-only version. With this one, you can only compare them for equality. Now, comparing for equality is still a very powerful thing. I've got a secret name. I give a copy of it to a select few, and only they can present it back to me, and I can verify that, yes, those 2 are the same. So it's this bearer token for an authentication-like purpose. But that bundling process there is useful. Ground terms have both read-write bits. Oh, this is not true. This was the one that I wanted to fix. Ground terms have both read-write bits on. This slide is false. Ignore it. Ground terms of the form row:, this is a URN, may be registered if certain proofs are supplied. So say we've got a domain like google.com. Google.com would like to have some name that everybody can know about, but only they can listen on. So they register row:, google.com. And the way they prove that they have ownership is they put a DNS record in that has some, we hand them a challenge and they put that as the response, and then we verify it. Similarly, you can register a public key. Put your public key in there, and you provide a signature showing that you have the corresponding private key. You can get a name where you would like to have a public contract. You supply the contract, which you have hashed, and stick the hash in here, so you know a pre-image, therefore you can register that name, and you're the only one who can listen on it. Registering the URN allows others to look it up, so they interact with the registry. They say, give me the name that I should use when talking to this URN. Usually, it's someone is deploying a contract at that name, and so they want to be the only one who can listen on that name. They don't want other people intercepting messages meant for them. So when a client of that contract talks to the registry, they get a name that can only be sent on, with one of those bundle pluses around it. That way, anyone can send to the contract, but only the contract can listen for those messages. There is, however, another way you could set it up. If you're supplying a data feed, you want to be the only one who can write to that data feed, whereas anyone should be able to listen. So you get to specify which name the client gets in response. Oh, and the reason we're not sending directly on the URIs themselves, or URNs, is because when a domain changes hands, if somebody else acquires a domain, they want to be the ones who control which contract is running there. And so the registry can be updated, whereas contracts deployed at a particular address can't, for the most part, by default. Blessed contracts. We've got the rev contract, the registry, Casper contracts for bonding, unbonding, slashing, and distribution of funds. These are all blessed contracts in that they don't require Rev to run, or phlogiston. Every node has to implement them. It's just part of running the software. Sometimes validators will go offline. New ones need to come online. So when a validator bonds, unbonds, or is slashed, everybody needs to know about it because every validator has to know about every other validator. Now, the simplest way to do that would be to publish a transaction in the top namespace. But that's not technically necessary and requires a lot of validators to participate in it. What you can also do is send lots of independent transactions to namespaces that are high enough. And by high enough, it's, say, namespace A, we suspect of having a coalition of validators within that namespace that will reject things they don't like, and one of those validators is to be slashed. If we just did it in the namespace A, they would reject that and continue processing, and it would cause problems. So we want to do it in a namespace that's the join of enough that any particular namespace, if we suspect it of having a coalition, can't overpower that transaction or reject it, but not necessarily at the very top where everybody's participating. That's all I've got for the regions and namespaces, but I'd be happy to answer any questions that people have. Oops. Oh, well. There we go.
There's a mic.
Yeah, there's a mic there on the side if you want to use it. Okay, everyone under, yes? Can you use the mic so that people on the recording can hear?
Jamie, the delegate from Seattle. No, okay. So I saw that you created, or there's the ability that two independent namespaces, if there's a need for the two to create a connection, a bound to bind them, that it creates an independent, somewhat kind of secret namespace that it's only shared
No,
between
it's not
those?
a secret namespace. It's a secret name in that namespace.
Yeah, but it's joining two. Same delegate. So it, yeah, I don't understand because like it's the two will be independent namespaces.
Yes.
But I need them to connect. It's created. It's moved to the namespace where it's going to
Okay,
execute.
so let me give an explicit example here. So one of the things we've got is the idea of a coin purse, which holds the value. That's all done with essentially object references. These are names that are passed around internally. They probably live at an unforgeable name. So there's no way to talk directly to a coin purse unless you've been handed access to it. However, you get two guys meeting on a street, they want to communicate even though their blockchain wallets don't know anything about each other. They're blockchain coin purses, sorry. A wallet is something that contains a coin purse. So my first wallet was billfold here, but it had this little pocket for the coins in it, okay? That's what we're talking about, a coin purse contained in a wallet. The wallet itself is a contract running at a public name that's registered, and it uses one of those row colon URNs. It's registered at a hash that anybody can hand off. But what it does is listen for messages, and anyone can send it a message, but it also checks that that message has been signed by the owner of the wallet. So in this way, the owner of the wallet can say, transfer to this other wallet that's identified by this hash some certain amount of money. And so then it checks that that message that the owner has sent to it was signed properly, and then continues using the using the hash of the other wallet. Now, only some of the methods need to be signed, the ones that say send money over here. Some of the messages are available to anybody, unauthenticated, that say something like, give me an unforgeable name by which I can communicate with you. So I send something here, I sign it, my wallet validates that it's from me, and then talks to the unauthenticated thing on the other wallet saying, give me a name to talk to you by. So by using these public names, then they can establish the first part of the connection. Then when they want to interact with each other doing code that's not just this mobility stuff, but running code in the same namespace, they can use the Diffie-Hellman-like construction to create two names, or create a single name that they both know in that secondary namespace. Did that answer your question? Where'd Jamie go? Yeah, there he is.
Not sure.
Okay.
No, don't give up. Keep going until you're satisfied.
I mean, we've got plenty of time.
Well,
I guess part of what I don't understand is, so something is created that's then the mobility element, and then that is deprecated. It's removed from the
Yeah, so
the namespace it's
communication
created in.
this way,
But there's not like an actual separate or new. One of the things I was envisioning was like this incredible rampant situation of lots of namespaces being created by entities in separate namespaces trying to connect to each other. And so that was, that's kind of where I was going with that. Dropping the mic.
So the namespaces always exist. There are if you have n regions, there are 2 to the n namespaces. That's just the way it's set up. Ideally, most of them will be empty, but they always exist. So that's the first thing. And so you're not creating namespaces in response to things. You're creating a name that lives in the right place. That place already existed.
now this version of namespaces is the very simplest, stupidest thing we could do that still supports sharding. For Venus, we intend to have a much richer notion of namespace based on behavioral and structural types, something much closer to what you were expecting, I think. But this suffices for getting the network up and being able to shard and do that. And since we have such a tight deadline of the end of this year, this is the one that we're adopting.
Mike, can you draw the lattice for people
Sure.
so they can see how the regions are constructed and how to calculate which validators are in what namespace? Maybe on the big board.
Okay. Wobble, wobble. There we go. So let's see. You can think of this as being the vertices in a hypercube, and to keep it visualizable, I'll stick to 3. So we have this bottom namespace here. There's the namespace, say A and B and C. Here's B join C. Here's B join A. Here's, actually I should put these at the same level. And here's A join C, and then each of these there with top. So here is the top face of the cube, here's the bottom face of the cube, and then various sides. If you have n of these, there are going to be 2 to the n vertices in this cube. So in this case, there are 3 regions, and we generate 2 to the third is 8 namespaces.
What are the A, B, and C going to typically represent? Like, those are the regions, right?
Yes, these are the regions. Regions, we haven't decided what exactly the regions are going to be. One reasonable proposal would be to have them be geographic regions, so like North America East, North America West, Europe, Asia, something like that. But there's also the possibility of having local neighborhood regions that could be added. We haven't decided yet. We know that Pyrofex is intending to deploy hardware to serve at least some initial subset of regions.
So one thing that's critical to making this work is to remember that although the namespace is called B join A, the names in that namespace are disjoint from B and from A.
Yes. So you can have X in A and X in B and X in A join B, and all of these are different X's.
Well, but just also that there's no overlap. There are no names that every name lives in exactly one namespace.
Yes.
And so it doesn't live in any of the what you might consider, sub pieces in the lattice. It doesn't live there. It only lives in its specific slot.
Hold on. Greg, nobody can hear you on the recording.
So you can think about these as qualified names, right? So a fully qualified name mentions the region in which it's residing.
I think Pavel had a comment.
It was more a question than a comment, and please don't facepalm because I was late 5 minutes. So I have a very basic question: how the name becomes part of the namespace? Like, what's the construct? Like, how it's like?
Well, for names declared with new, they look like private UID and namespace. Private is not something that you can type into a contract, so this is unforgeable in the same way that you can't take an integer and turn it into a Java reference. This is the integer in that example, and this private construction is how the state of the blockchain represents the reference.
No, I think my question was more general. So if I create a name, if I use a name, it automatically is some part of a namespace, or it has to be used as private keyword?
This private keyword isn't part of the grammar, so it's not something you can type. It's just what's stored on the blockchain. Kyle?
How would you write code that got a name in a particular namespace? I think is what he's asking. Like, where you show him the new syntax, the straw man.
Okay. So at deployment time, you can choose a namespace for your contract to run in. That will usually also involve interacting with the registry to get a particular name there. But let's say you've already got some code running in namespace A. Then you can say new x:b in xbang q. So this creates a new name in the B namespace. And then you can send on it. And then this code will do that code mobility thing that I drew earlier and move it over there once it gets to that point.
What's the motivation for putting name and then namespace as opposed to namespace then name in new?
It's like a type.
Okay.
It's the beginning, very, very, very beginnings of a type.
Okay.
Yeah.
So yes, it's the beginnings of a type, and in math, they tend to put the type after the thing. In C-derived languages like C++ and Java and so on, they tend to put it before. It's arbitrary. That's the one we thought of. Yeah. Scala tends to put it afterward, and the rest of our code's in Scala. Yeah.
Fine with me, obviously.
So I think I have it all right, understood, but just one question. So namespaces, if I understand correctly, they are bind to regions, right? Like how the namespace is constructed depends of how many regions we have?
Yes.
Okay.
So Gary is watching online and has a question for you to go back over bundling and why do we need it?
Sure. So in the language, we have a construct match P case and then some pattern. So often we'll use, say, a list. Let's see here. I'll just say foo. So this says if the process P is a list containing exactly two elements, the first of which is the string foo, the second of which is some variable, is some other value, and we're going to bind this variable to that process. Then we're going to do Q with it, and Q presumably will mention arg1 here. So this is similar to the switch case statement in a language like C or Java. It's much closer to the pattern matching abilities of Scala. But this is called a destructuring assignment. It takes apart P and binds this variable to some part of it. Now, this pattern language is not just lists or data structures. It's the entire grammar of the process. So if I had some process like this one, for k from x, if k double equals secret, then q. This is something that we don't want to leak. Now you can view this on the blockchain, but it's going to be of the form private something or other, so nobody can make this. But if they said match P case this thing, secret is now a free variable, and it's comparing this to the process it received, and then in here, this process R can mention secret, and it has extracted that from the code. We want to prevent that. So what we do, if we ever want to send code that looks like this thing here with a secret in it, we say bundle this with some other thing. No, I guess we don't need the some other thing. All we can do is grab this as a whole. We can no longer take this apart and extract secret. This new process behaves exactly the same as this one, but you can't do a match case on it. Henry?
So am I right that essentially this is like the attenuator for authority in that sense?
Yes.
Yeah.
It attenuates the authority to do destructuring bind, destructuring composition. It also gives us a place to stand so that if we quote this thing, we have a way to do plus or minus or 0 to attenuate the ability to send, receive on the name. So bundle is an attenuator in that sense. Kyle.
I just wanted to point out why you want to tie it to bundle, because if you don't, somebody could then take apart the name and then put it back together, like with more authority to read or write. So for anything that's multi-part, if you don't tie the permission to send or receive on it with up with bundle, it's self-defeating.
Yeah, so say you had some process P and we had restrict instead of bundle. Restrict plus of P. If you can construct P from its parts, take it apart, get each part of P independently, then put it back together again, then you've created a name that is no longer restricted. So only bundle can enforce this restriction. Yes.
Can you talk a little bit about the namespaces where the blessed contracts like Rev are going to live, like the top level purse?
Each of the blessed contracts runs in every namespace. So there will be a different Rev contract running in the namespace A and B and A join B. There are three instances of it. They're necessary because they, it's necessary to run them in each namespace because each of those blessed contracts are necessary for the operation of the blockchain. I guess registry technically isn't necessary for the operation of the blockchain, but it's necessary for any useful operation of the blockchain.
Any operation of the blockchain that deals with the outside world.
Yeah, anything that involves the outside world.
I have a question for the group. How many people feel they can walk out of here and say, yep, I got namespaces. I get it. I'm comfortable, I'm happy. Okay.
Not enough.
Yeah.
There are clearly some more questions.
Okay,
that need to be
so you
answered.
need to be asking questions. Yeah, don't give up now.
So I'm sort of understanding namespace as some sort of execution environment where you can access these different names. But when you're saying that the names are disjoint for every namespace, then what is this hierarchy really for? I mean, the validators are accumulating as you go up, or they're sort of being ordered by inclusion. But what about the synchronization between different namespaces, the mobility that you were talking about? Is that also something that's going to happen on a level up?
So when I wrote X in A and X in B and X in A join B, what I meant by X was if you say new X while running code in any of these spots, or if you explicitly said new X colon A, this X is only bound in here. What actually gets generated there is something in the form private UID namespace. And because they all have these different UIDs, they really are distinct. It's just that the name I'm using within this block happens to be the same. It's just as, this X in this block is, despite living in the same namespace, is different from the X in this block. They will have different UIDs. Does that help with what you were asking? Is there?
No, he's asking about the lattice.
The-
So in A join B, what's the relationship between X and A join B and X and A?
So private UID,
Like if they are disjoint, why do we have a lattice? What's the inclusion of A into A join B?
I think I can help with that. So if you run something in A join B, it's synchronized relative to things that happen in A and things that happen in B because it has the same validators. In order to, that synchronization is exactly why they have to be disjoint, and there's a subtle proof, but if they're not disjoint, then like either one side can bully around the other and force them to throw away work or force them to suspend indefinitely on some computation. But if they're disjoint, like you don't have to wait for the laggards. except for things where we're both waiting for each other. So the synchronization is why you would put it in there. Is you want to synchronize with relative to A and B. So if you have assets that live in A and then end in B, you might do the exchange in A join B, and then you can push the resulting value back down to A and B.
There was a time when we were considering the notion of a join block. That is, A is doing some computation along here, B is doing some computation along here, and then they wanted to interact with each other. And so we would propose a block that's in both of these. The problem is, if you have to get consensus on this block between both, one of them can bully around the other one and say, I'm going to wait a long time before putting consensus on this. So either I am if A is bullying around B, if A says, I'm going to wait, either B has to wait until A gets around to it, or B speculatively executes, and then A says, okay, after you've done all this work, I'm going to come along here and change the answer you thought was there, and so you have to throw all that away. So that's why we're keeping them separate and having this code mobility idea. And then if they want to interact, they construct names in the namespace for both of them to participate in. But if they're doing work in A join B over here, and A and B are both participating in that, they can still continue doing their work in their own namespace independently or with any other region. So if A is trying to bully around B, all it can do is prevent progress in the namespace A join B.
So if anyone's following Vlad's development on his notion of sharding, this is a distinct departure. And I was hoping Kent might be here. He might.
Kent's not showing up till Monday.
Oh, okay. All right. Kent can speak to this much more directly, but this is a distinct departure from the sharding direction that Vlad has been considering.
So how are the namespaces A and B informed by what's happening in A join B?
So A, B, and A join B are separate namespaces, but A has a set of validators. Is my mic on? No. Claims to be on. Oh, there it is. Okay. There's a set of validators corresponding to A. There's a distinct set of validators corresponding to B. Both sets of validators together validate the things in A join B. Does that answer your question?
It feels like it's the beginning of an answer. So I have some exchange happening in A join B, and it refers to the assets in A and in the assets of B. And so how is the information that an exchange has happened, for example, in A join B, being transmitted back to A or back to B?
The way that you would do it is you would move the assets from A to A join B.
So,
and then do the exchange, and then bring them back.
So for example, there's a sell contract that you can find that we've gone over before in other spots, but the signature looks like sell, get, set, contract, equal, oh yes, and state. And in here is the code. But these names are how you interact with the cell. I want to get the current value of the cell. So I send it a channel, the return channel, and then it sends on the return channel the current value. For set, it reads the value of the state and then puts the new value on that channel. State is the namespace in which the value of this is a name in the namespace on which the value of the cell is resting. So if in here we had if we had one more, comma, move. If we had this move instruction, then we could listen on move and say, whenever I get a name here, I put the state at that name instead. So I can move it to the namespace A join B by providing a name in that namespace, and then send back to the invoker of move new get, set, and state names to interact with it in that new namespace. So there's a way of reissuing this contract in a new namespace. That's an interesting departure from the way Ethereum does it. The only way you get a contract running on Ethereum is by deploying it. In RChain, you can create a contract and deploy it, but the continuation of the contract can contain many other contracts, and those contracts can move around between namespaces, can go all over the place. So it's possible to move where a contract is running, to move where code is running. Now, the reason that you would want to put it in the namespace A join B, rather than only doing this code mobility thing that I drew earlier, is that for code mobility to happen at all, you need to reach something, finalization suffices, but something close to it, where nodes judge it as being safe to act on it. Whereas things in here, you can run as far forward as you want, and have both of them interact and roll back and do things together, achieving consensus there much more quickly than you could before. I mean, by interacting between the independent namespaces. Any other questions? Anything else from online? Okay. Dan.
Yeah, you made a sort of a postscript about how this is the simplest thing that could get the project off the ground, but in Venus or something, you expect to do this behavioral and structural types thing. That might have been, if you're doing this publicly, please make that a preface instead of a postscript.
Okay.
Because I had been sort of looking at this namespaces as these types and things like this, and then I saw this, and it's like, are we still, is this a different use of the word namespaces? Are we still, so.
So when there are a couple of different conceptions that are going on here. One is the namespaces just as a collection of names, okay? And then collections can be specified in at least two flavors. One flavor is extensionally. I list them out, this URL and that URL and that URL, right? So that's extensional specification. Another specification of a namespace would be all the URLs matching this pattern, all the URLs matching this other pattern. That's intentional descriptions of the collection, right? So the namespace's paper, namespace logic, describes that. Now, that's independent of the next level of specification, which is how do those things line up with validators, right? And so this is giving the minimal amount to line those up with validator sets, right? And then once you have the line up with validator sets, you can go from, basically a namespace with no structure on it, so to speak. This namespace is all the names ever that go with these validators, right? To something that has more structure in terms of predicates. All the names that match this pattern and go with these validators. Does that make sense? Does that help?
So I take your point. I agree. I should have clarified. These are what I might call regional namespaces. It's how we split up names among the regions. Within a
parochial namespaces.
It's just saying this is the same story you've been hearing for years. In other words, we're not taking, that's what I... Yeah, so we are also going to support intentional namespaces that in a contract we can write contract foo and then put patterns here. not just variable names. And those patterns will filter messages coming in. And so they behave as intentional types in those positions. For structural typing, we don't yet have the behavioral patterns yet, but that's coming in Venus. Chris, just a sec. Christian, sorry.
So, so what exactly is the role of regions, and how do they change or interact, or be created or destroyed? And and if they are as fundamental to this idea of namespaces, I'm surprised that y'all haven't decided what they're going to be yet.
Well, excellent questions. The reason we haven't decided what they're going to be is because it is a very practical question. It is, how do we want to design the network so that we get the best performance? And in order to decide that, we need to do a bunch of actual testing of the network as it is built, but we're not there yet. We don't have the software written to the point where we can test how the network interacts. Regions practically are there so that we can reduce the time required, the latency between a client and the blockchain itself. They're also there so that we can split up the blockchain, or block DAG, into pieces so that we don't have to have the entire network agreeing on what happens between just these two guys over here when nobody else cares. It's only once they start trying to interact with somebody farther away that happens. So if you look back to the age when there were local banks, that some guy, rich guy, would get together and put up some funds and then interact with the community, and he would loan to somebody because he'd known the guy for 10 years. All of that economy was happening within a particular neighborhood. And it's only when you wanted to interact with some bank somewhere else that you'd use the Pony Express and exchange letters of intent and cashier's checks and so on. And that is the kind of structure we're building here with these regions, is that a region is roughly going to be a geographic location where people are expected to do business with each other. Now, of course, part of the attraction of this blockchain is that you can do business with anybody anywhere. So we also are considering the idea that regions can be organizationally based, that a global business may have its own region for internal operations that it's doing between its arms. So these are considerations that we're thinking about, but until we've got a test network up to play with, they're really hard to decide on what's going to be best for the system.
I mean, in typical network design, this is very much a tunable parameter, right? Sharding geographically, sharding in terms of business, sharding, by last name. These are tunable parameters that are, really you discover, and we don't have enough up and running to be able to discover the kinds of things that we need to discover about, how to lay this out against actual usage. I want to just throw out here, in connection to kind of a pet idea of mine, that I think when we start talking about the staking validators in the Genesis blockchain, that's a significant opportunity for the RChain network. It's probably one of the most important decisions that we make with respect to securing the network. And I think we should be looking at how to secure that across lots of different ways of carving up that space. So for example, we might have cities around the globe be staking validators. We might have other kinds of governmental layers be staking validators. We might have high-profile individuals be staking validators. Jay-Z, Bernie Sanders, right? and I'm not joking. But the reason is because you want visibility, like vested visibility on the network. And so these different considerations are going to also turn into how we tune how these regions lay out. Does that make sense?
So another thing we can do is, if we want to divide by region, that's great. If we want to divide by org, that's great. We can take the product of the two and get a set of regions this way, or 3 or n different ways of doing this. So we can create lots of different regions if we want to. I think this has got to be the last question because we're running out of time.
Okay, this might be kind of basic, but is it possible to have multiple namespaces joined? I mean, the examples we're using are pretty basic.
Sure,
A
if
and
we
B,
have
B and C, but it could
A
be
join
A and B,
B
and
join
Q.
C and B join D join F, we can join these to get A join B join C join D join F.
Those are 3 different ones.
Yes, this is one namespace. This is another namespace. The join of those two is this third namespace.
And you have all of those, right? Like
Yes,
from
all
the
of these
beginning,
exist.
you get all the combinations of all the regions in the lattice.
So if we have 256 regions, there's no way that we can explicitly list these because there's 2 to the 256 of them. But at any point, some sparse subset of them will be in use. Great, thank you very much.
Hold on. So
Yep.
At this point, raise your hand if you feel like you understand. Slightly better.
About double what it was before. Well, that's good. Thank you.
So I guess we'll take 5 minutes, and then Kyle's going to present on behalf of Mike Birch regarding the RChain state, blockchain state. Birch's flight has been delayed twice, or canceled twice, so for weather.
Got snowed out twice.
All right, good. I hope you're ready to give the talk. Yeah, I was about to say. It's fine. I think I have a way to charge for storage. I think I have a. Yeah. I do. I'm only going to present on compute today, and then at the end I'll give a little bit what I had. But essentially, if like how I'm viewing the state anyway is as tuple space and then giant Rollin expression, right? So compute, we charge for stuff that happens in the Rollin expression, and then storage, we need to charge for state changes that occur in the tuple space, right? So essentially, when I add a new name to the tuple space, I associate with it a storage ticker, right? And while the ticker is above 0, okay, then all traffic over the channel is permitted, right? When it reaches 0, I freeze the channel, and then for any events that come in, I log them, I send out a refill request that comes back with more, then I can execute the backlog and keep going. So that way we don't have to do storage for every process that's in the store. We can just limit it by channel. Yeah, and then contract names as well. So like your contract name would, yeah, so.
No, that's good, that's good. I have to think it through, but yeah, that seems.
Yeah, I thought I'd bring it up in the breakout session.
Yeah, that's a good idea.
Yeah.
Good idea.
And then check. Just talking to it.
Hello?
Yep.
Oh. HDMI. Oh, wait, I might have. No, it's mini display port. Oh. I wouldn't know how to use it. I mean, I guess, but. Or is. Hold on. Well, let's try this one.
It does have a small monitor, so
Oh, it's probably some Mac only thing.
Huh?
That it would not surprise me if that were some stupid Mac only thing. It's mini display port. You just want to, Mike, just want to bring up your laptop and I'll present.
Greg, I like how you get people to ask questions. That's how
I think I need to plug this in order to see my login screen.
Why don't you just go ahead and open up the presentation. I'm just going to use Mike's laptop. Do you need power? You're fine.
Looks like that. Make sure that this loads up.
You're on the wrong one. We'll let him in a bit.
That's a Thunderbolt, but you need
HDMI? HDMI will work too.
Yeah, HDMI.
Wait, weren't you just here?
Yeah.
Did it just
But
work for you?
it said this one's dying. So
This cable itself is dying. This looks like it's like yeah, DisplayPort cable, like whatever. Okay, so we'll just use the HDMI for now if we can. Okay. All right. I have HDMI too.
Yeah, I have HDMI as well.
You want to try your laptop?
Here, try yours.
Yeah. Let me try mine.
It's not going to get easier on Linux.
Well, Macs are happy when you use all Mac things, and then they flip out when you don't. I don't know. Okay.
Let's see, so you're going. Oh. Is this the only output you have on here?
Well, there's DisplayPort, but this wasn't working either.
Oh, it wasn't? Well, the projector was, for whatever reason, got turned off. So let's try this again.
Want to try the other one again?
I don't know. I've never presented with this laptop, so I don't know if it even works.
Mike, bring your laptop back up here, please. Michael, bring your device.
There it goes. F5.
I don't know. try view present or something? Yeah. Command enter.
Is F11 like
view
full screen?
Yeah. You have to actually click. It should just be just right and left.
Yeah. All right, so I'm doing Michael Birch a favor because he was snowed out twice. He's still stuck in the airport. Yeah, he's watching me slaughter his presentation. So.
We have a camera on him as he arrives.
So if there are flaws, they're probably mine. On the plus side, there are some things where I was looking through and that he'd written things that aren't quite correct, and I'll have the opportunity to just point them out and fix them as we go along. So we're going to quickly go over Rollin just enough to understand what goes in a block. We're going to talk about the RChain state, blessed contracts, and the block structure. And I'm going to gloss over Casper because that's the part of this presentation I understand the least about. So Rollin is a parallel programming language. There is no semicolon. There's only parallel. And if you need something to occur in sequence, you basically have to make it have a data dependency, or there's no other way to force things to be in sequence. So there's sends and receives, news, and there's some other things that, but these are basically what sends and receives are what matter for the blockchain, because everything else gets evaluated down to sends and receives that are waiting, and that's what forms the state of the Rollin or of the blockchain. So names are either quoted processes or unforgeable. That's not quite all names are quoted processes. There are just unforgeable processes. When you create an unforgeable name, it lives within a scope. Scopes are something that you've seen in lots of other programming languages. So contract definitions create a replicated receive along with, there's a semantic difference in terms of payment, but we're going to gloss over that for this presentation. And so when a send and receive meet, it produces a COM event, and those are the things that are going to go in the transaction ledger in the blockchain. So what is the state for the RChain blockchain? The state is one giant Rollin term. That's it. So it's interesting, though. Mike and I sat down and we realized that there's a subtle distinction between, like, a lot of times in pi calculus, you're given one giant term, and thus shall it always be, and then it reduces. And in our case, we also have an event called deployment, where you take the term and you add new things on it. And it turns out that you can't pretend that the term was always the new term, because things that reduced one way and then you add something on, well, if it were the whole term to begin with, it could have gone the other way, but that's not how we're not doing it that way. It's just you put new things on, you change the existing term as it has reduced to a new term with some additional stuff, and now that term can reduce further. But we never go back in time and try and, like, oh, well, this could have matched over there. No, that leads to killing your own grandfather. So everything is one big Rollin term, and that Rollin term can change, and the way that it changes via deployment. And that is the only thing that So it changes via deployment, and then after deployment, it reduces. So that's how you interact. So you deploy, S goes to S par P. You pass on basically how you're going to pay for what you're deploying. And that arrow is not the same arrow that you would, it's not a reduction relation. This is, it's one level outside of the reduction relations. You can basically deploy any valid Rollin code. And we'll talk about, so you don't have to just deploy a contract. You could deploy things like, if you have a wallet, you could deploy a message along with its, a send that includes some instructions and a signature, and then your wallet does the thing that, so you didn't have to deploy any new contracts. You can just deploy a send, which would act in a lot of ways like a method call in some other environment. So the blockchain runtime environment will be different from the interpreter. For instance, what does it mean to write to standard out on the blockchain? There isn't going to be a standard out. There are things like different things will be active, like the rev contract, the registry, and yeah, unforgeable names are unforgeable. You can't produce, you can see what it is. You can go look at the block and you can see what the name is. But because of the way that you write Rollin code and send it to validators, there's no way to produce the unforgeable name. It's actually kind of magic. I mean, it's straightforward how it works, but it's really kind of cool. Like, what do you mean it's unforgeable? I can look. I can see exactly what it is. Yeah, but you can't write it down. Yeah, you can't write code that that contains it. Yes, that would be something that we would consider equivocation. Is if you produced if you forged an unforgeable name, then yeah, you're not Don Quixote. You're just slashed. So blessed contracts. Like Mike said, no one pays to run the blessed contracts. You might have to pay to interact with them, like it's listening, but no one pays for their storage. So they perform certain system critical tasks. The rev mint will be a blessed contract. The registration contract and the proof of stake contract, and possibly others. So blessed also means that certain parts of the system will look at the contents of that contract and make decisions on it. So the proof of stake contract is the blockchain visible part of the proof of stake algorithm. It's the part that has to come to consensus. It's the mushroom part of mushrooms grow underground and then they like pop up and you can see only a part of, anyway. So the rev contract, we should have a session on in the breakouts about how mints are different, how they behave, things like spawning purses and absorbing purses, and like, because that's kind of, it's likely foreign to people that have seen like Bitcoin-based triple bookkeeping, or even like a ledger-based one. It's kind of a strange object capabilities hybrid of both of those. The mint has the authority to produce non-empty purses, basically to create new money. Purses have the authority to produce new empty purses. They also have the authority to produce new full purses as long as there's a conservation of value. You can take a purse, you can a $100 purse and split it into two $50 purses. What you can't do is print a $100 purse. That's what the mint does. The way that you handle authority is unforgeable names. We talked about that. So Michael Birch we have some initial work on the Rev Mint contract. The other thing is we will encourage people when they create non-Rev assets to use this because this is the kind of thing that will allow you to scale exchanges in any of the namespaces and do them quickly. And so we'll encourage people when they create their own assets, we'll be setting the example of this is the way to do it so that it will scale. So Mike Stay talked about purses versus wallets. You can take a purse and you can wrap it with a signature verification, but you could wrap it with other things as well, like multiple signature verification, right? Like the same underlying purse code just needs a slightly different wrapper, and now you have a multi-sig wallet. But you can also take the purse and have the purse owned by a lottery contract or an atomic exchange contract. So purses can be wrapped up by multiple things, and they're a really useful building block in how to do exchanges in RChain. All right, so we're going to send Bob 10 Rev. And I'm not quite sure I'm not quite sure what he's doing here, but so I'm assuming that. So the first thing is that address is public, and like Mike said, it would live on the bottom namespace and never do anything. So instead, what it would be is you would send that to the registry, get back a result, and then do this. Do that same send on the resulting channel after looking it up. And there's a subtle reason why we want it to be that, and during the question portion, I'd be glad to explain that. So basically, we do a signature check, and then if the signature matches, we do what's on the next slide. So this would be inside of that block. So basically, we create a new empty purse. We deposit 10 Rev in that purse, and we give the entire thing over to Bob. And then presumably, he's going to immediately empty it. So I guess you could write code that did nefarious things, that took that purse and gave it to Bob and Fred and George. But the nice thing about Rollin is that only one of them is going to be able to succeed at emptying that purse. And then they'll have evidence that you're a big fat cheat. And they won't deal with you anymore. It's not, none of the validators have done anything wrong. But the validators are the ones that catch you to prove that you've done something wrong. So you can attempt to double spend, but you'll get caught. So the registry contract allows you to take and do a lookup from public names to private names. It's just one giant map. And there are rules for creating entries in the map, like Mike said. IANA, pub key, and hash. And We might consider others, but those will be we will at least have those. So unregulated public names would be user owner friendly, and that's why at the moment they go to the circular file, the trash can. We won't prohibit it. It actually could be useful we will record and then discard rights to public names. So you could write to a debug channel and then watch the blockchain, and we will record the fact that you sent to the debug channel. We just won't do anything with it. This would be one way that you could have local code interacting with the blockchain is you will see the rights. When you see that a right to a public name has consensus, you can pull that out. But the thing is anybody can write to a public name. So it's not quite unlocking. Instead, it's a lookup. So if you try and do what was here, that right will succeed, but it won't go anywhere. It'll go to the circular file. The reason that we wanted it, I will explain that later. We have hashes, public keys, and IANA. Although I don't know that we'll use URLs, but instead they'll just be the domain name because of DNS records. So this was actually an interesting example. The first example, if you were to deploy that, it constructs a contract listening at an unforgeable name. When we get the garbage collector done correctly, we will see that no one can ever write to that name, and we'll just throw it away because it's equivalent to nil, or it's behaviorally equivalent to nil, because nothing can ever make it do anything. So, and then, yeah, the registry example isn't quite right. So, what is he doing here? I had a harder time with this example. I'm sorry, Michael. He's what? So basically, when you deploy it, you could just, we will have the ability to say, yeah, register and it'll be straightforward to deploy a contract, and we'll actually have tooling to make it easy to say, well, just take this contract and deploy it and give me back the hash so I can publish it on my website. Like, I don't know that all of that will be straightforward and like well documented so that everybody gets it right. And ideally, the software will just have like that as a default. Deploy this contract and register its hash. All right, so the proof of stake contract is another blessed contract. It handles bonding, unbonding, slashing, and rewards. So there's more details. One of the important things to note is that there is necessarily a delay between unbonding, or when you stop being a validator, and when you get your money back. The reason is that that is the amount of that time is the amount of synchrony needed for the network. And we can talk about that at the breakout session. But if you immediately get your money back, you have the opportunity to start lying, and they can no longer slash you. So you can produce alternate histories. So the proof of stake contract sets all of these things. It handles bonding, unbonding, and staking, and bonding and unbonding, and the delay, and slashing. we'll use the same purse contracts for bonding. So what will happen is while your stake is bonded, it will be held in a purse that you don't have access to. And then after you do that, you get added to the validator list. Like I said, the other part of what it means to be a blessed contract is the Scala part of proof of stake will inspect this validator list. So that's part of what it means to be blessed is you'll go in and you'll look at this particular list. So you call to unbond you call the unbonding contract with the signature return channel. So after that you become an inactive validator, but you can still be slashed until you get your stake back. Slashing is interesting because a portion of that that verification will be done not in Rollin. But the actual signature and purse distribution, whatever we decide on, will be in the blockchain. So the validator will be required to have cryptographic evidence of the offense. Any validator can slash any other validator. That's one of the things that that you need to know, even if you're not in the same regions. So equivocation, creating an invalid block, failing to meet the performance requirements. The performance requirements will likely not be burn it to the ground slashing, but like equivocation just will be. So yeah, and once you're past the unbonding waiting period, you can hand the proof of stake contract a wallet, or you can use your wallet to hand them a purse, and they'll transfer the funds back out. So the blocks. Like I said, the state is the set of Rollin terms. So what's in a block are the post state, what code was deployed during that block, and the reductions required to get from the previous state to this state. Included in, and there's the header will include a pointer to the previous block that has that root hash. We're going to use something like a Patricia try to handle the state. And so as part of that, we have deterministic serialization of Rollin terms. All right. Sorry. When Michael gets here, he can give this part of the talk. So I'm going to wrap it up here. If you have any questions for me, I think I said I'd cover something in the questions part, but I don't remember what it was. So this is your time to repeat it back to me and tell me what I need to tell you. But thank you.
So that was distribution of funds. Alice is sending 10 racks to Bob.
Raise your hand if you want to talk.
I just had a question with respect to the block structure. You say that you include the post state, the new code, and the receipts of all of the synchronizations. Why do you need the post state, aren't you going to be able to find that just by looking at the parent hash and getting it?
Technically you could, but it's good to have, like, it's there as a check that, like, yes, I got to the same place.
Making it explicit.
Oh, okay.
Explicit transactions complete.
Okay.
Mike has an answer, I think. Here. I'm not using this one.
It won't be the entire state because the entire state is going to be very large. It's just the delta of the state, right?
No. We'll have the root hash of the post state.
Oh, okay.
In state-based change, this is actually a very common thing. You have the transactions of what occurred and the new post hash. So, like, for example, if you wanted to come up to speed, right, like, and you knew you knew which block you wanted to come up to speed from, if the post state is in there, you don't have to go back to the beginning of time and follow all the transactions. Somebody can just start giving you the pieces of the Merkle trie, and you can use the trie structure to know that what they're giving you is the right stuff. So
the thing you were going to go back to is how mints work and can be distributed among namespaces so they scale.
All right. Oh, yeah, I'll come over here. Oh, yeah. I'm just going to do kind of.
Mike Birch says the post hash is for giving short proofs that you have the right state.
All right. So here's a purse. I'll just write a money bag instead. So the mint lives in A. But you can, so the way that you create an empty purse is you ask the mint for an empty purse, and it will gladly give you one. You don't need any, you don't need to be the mint owner to get an empty purse. So a purse comes empty. It has some methods, but the important characteristic of a purse is that it can tell, right, like, I can construct a different mint. So the most important logic of a purse is the ability to tell that this is not that. It solves the alchemy problem. So we can call this is mint gold, and this is mint lead. Right? We can't turn lead into gold. So, no matter where the mint lives, you can create a new purse. You can say, create me a new purse. And you can give it the name where the purse will live. And it can construct derived names so that everything lives in the correct spot. And then, so even if this is in A, so if this is in region A, right? The purse can live in region B. And then you can create another purse in region C. And then it's straightforward. You can set up an exchange protocol so that you can so you have, all right. So if you wanted to do an exchange, what you would do is you'd spawn a new purse. So, all right, if this has 100 in it, and I'm going to send 10 to C, what I would do, I would split into 2, right? B with 90, and then B join C with 10. I have a new purse. It's living at the joined namespace. Right, and then to receive, C would do the same thing, right? C has X dollars, and then there's, C would create a new purse. Yeah. Although this step might not even be necessary with 0, right? Like, and then they would get merged, and then you would do code. You would take this resulting purse, and you would do code motion to move it back down, and then join it. So, like, the nice thing is, like, you know, that you don't have. There's a way using bundle. Bundle makes it possible to include with each to give each purse a little bit of code that can tell that it's not lead, and that code can run anywhere. And so you never have to go back to the mint. There's no central authority required to verify that an exchange occurred. Now, the central authority might want to watch all of the places that are doing these things to make sure that.
Set that up as a contract.
Yeah, but the thing is that it doesn't even need to be a contract, right? Because you can slash, any validator can slash any other validator, right? Like, as long as they're behaving, they can't break. You would have to have broken the rules in order to cheat. And then there's cryptographic proof that you've broken the rules. Thank you. So, yeah. So actually, I don't think this is necessary. We just use, so code motion to migrate down to C, and then we have all right, and so 10 plus X. So that's a basic block diagram of how you could do exchanges across regions with wallets, and then you never have to go back to the central authority, and this makes it so it can scale.
So you said that if the validator violates the contract, it gets slashed, and there's a cryptographic proof that he did that. So I can't imagine, like, what are the examples that the validator violated the contract at? I can't imagine how the cryptographic proof could look like.
By cheating, you have supplied the cryptographic proof because you sign all your blocks. So if you sign blocks that break the rules, you have just supplied cryptographic proof that you cheated.
Yeah, I understand that part. So if I supply the block that with the transaction that break the contract, so they break the rule of the protocol or the language, or like I imagine that I can't create the block that doesn't pass some the contract rules, like.
In order for a coalition to cooperate and give themselves lots of money, they would have to violate the language rules. So there's no way to have 10 evolve to 100 in the reduction rules of the language. So if they swap out 10 that they had for 100, then they have violated that and they can be slashed for it.
I remember one of the other things I was going to cover, which was why we decided that you don't send and receive on the row colon names. You just hand them to the registry, and then you either get back a response. And the reason is, I'm going to do this one over here. We'll leave my example up for now. So we'll show you the two different ways. So if I just allow versus
That says IANA colon row colon IANA colon pyrofx.net.
Okay. Oh, I put .com, but yeah.
That's a fireworks company.
So so okay. Oh, yeah, it's yeah. Right. Assuming I have some return channel already allocated, and then pipe 4. Yeah. Then, so the difference between these two is the meaning of this doesn't change whether or not this is registered. We'll have some ability to get a return or an error code if it's not registered. And so what that means is if it's not registered, the error code fires. If it is registered, this fires. Well, yeah, we could put it in a select once we get that working, or just make them mutually disjoint, like what will be returned. Yeah. Well, we have to garbage collect anyway.
I'll shut up.
So, but the meaning of this doesn't change whether or not this is registered, whereas the meaning of this changes whether or not this is registered. And what we didn't want was for the meaning of code to change based on what is on the blockchain. So this always means the same thing. It means try and get it the name lookup, and if it's there, send on it. And if it's not, don't.
And it also gives us a place to stand to get a different name when the domain changes hands.
Yes. Yeah, so if the domain changes hands, you can register a different name there. And then anything that still has the name register, anything that's still running that has a handle on the old name will continue to run. But anything that's deployed after that point, when it looks it up, will get a new name. This is also a way, this is just one reason why we might want UUIDs and not just hashes, is because that will allow you to update your code. And, I fixed the bug. Well, the hash changes, as it should. But it would be nice to be able to deploy to just a random UUID. And then when you fix a bug, you can.
Yeah, so it allows us to make two different kinds of guarantee. One is this code will never change, and the other is this code will always be updated to the most secure version.
Yeah.
Mutability, here we come.
Well, no, it's not mutability. It's the fact that what you get back depends on the state. But that's true of like all kinds of other contracts, right? Like,
You know, if I ask you for your wallet balance, like I'm going to get a different answer based on what I ask, unless you never spend anything. Right? Like I guess if I ask Satoshi's balance, it always stays the same.
Until it doesn't.
Yeah, well, when it doesn't, the whole world will hear about it. So that was, I remember talking about, saying I would answer that during question and answer. Are there other questions about what the state is?
So sorry, I have another question about the Mint contract. So the blessed rev is a contract running in every namespace. Is there one Mint contract for rev, or does each namespace have a rev Mint? Or yeah, what does that look like?
So
it could have a rev mint in every namespace. The reason to do that is not one of security, but rather one of performance, that you don't have to send a message across to another namespace and wait for the finalization sort of stuff to happen before you get your purse back. So this one can run, it's got the secret that's identifying it as gold rather than lead. Each one of those is done in that particular namespace.
yeah, when in order to have funds that only you control, you have to get a wallet directly or a purse directly from the Mint. You can't just, if somebody gives you a purse with $10, the thing is they still have a handle on it. So what you want to do is empty that immediately, and you need somewhere to empty it to. It would be very possible to attenuate the Mint and produce copies running in various regions that have the ability solely to produce empty purses. And so you might deploy like the full power Mint one place and an attenuated Mint in several places.
One thing that was on the slides here, to prevent hostile takeovers of namespaces, Birch proposed that there would be a limited number of validators per namespace, but we may use some other policies like having to pay every existing validator a fee as well as the bond, so that fees for attempting to overwhelm an existing namespace would be quadratic in the number of new validators, or we could make it depend on the number of validators, so it's cubic or exponential or whatever we want there. But that's one of the things that we haven't decided on yet, exactly how we're going to try to prevent takeovers of namespaces. Also, the Mint, if it has to exist in each region, would need to be magicked up as code gets deployed to a region, because we don't want 2 to the 256 copies of Mint code running.
Can I ask a question about registry? Is this on? Okay, so then will the registries be housed on a validator node within a namespace within a region? Is the registry going to be at a hierarchical level that's above all regions? I know last talk we were talking about all of row. Is that where the registry lives, up at that level, or are there going to be registries that are kind of more focused or more regional or more specific?
The registry is slightly unique because it should be the case that if I hash something and you hash something, that we just agree. So you can structure the registry basically so that you don't so I can basically look at something at some registry request, and we don't necessarily need to get consensus in order before I register something. I don't have a good answer for your question, sorry.
We got lunch.
So,
Raise your hand if you understood the majority of what Kyle's presented.
On the whiteboards or on the slide?
Yes.
well, we can do it separately. Raise your hand if you understood what I presented on the slides. And well, I didn't understand Casper, so like, right.
Nobody understands Casper.
So
I mean, this is
we'll let Michael present it when he gets here.
I didn't ask that question because Mike's here. Mike's not here, right? Kyle's kind of stepping in for Mike. So you're doing it.
Kyle's kind of doing a heroic job, just stepping in on a presentation cold, and so it's going to be hard for us, you know. And so what I would ask is that when Mike gets here, go nail him to the floor until you understand, right, what the content of the presentation.
Check. Some of the Mint stuff is actually, at least to my mind, easier to understand going through the code line by line. It's not that much code. 66 lines, he says. And I'm actually tuning one of my presentations. I might do a little bit of that. So.
Yeah, mints are actually straightforward to understand. They're not what any other blockchain has done, and so they're simple. They're not easy. That's actually the title of my talk. On rolling is simple, not easy. Because no. There's this talk about like that somebody else gave about simple and easy. Yeah, if you haven't seen it, it's definitely worth an hour of your time. He talks about easy means familiar, and simple means not a lot of moving parts. So rolling is very unfamiliar, but it's simple. So the mint model is, mints and purses are simple, but they're not easy because they aren't what any of the other blockchains do.
That's not to say that we couldn't do that. It's just that this scales better.
Yes.
By a lot.
It scales in two ways. Number one, you can spread purses over all of the regions. And number two, it makes it so that like, even within a particular region, if two purses are not, if two transactions don't interact, you can run them on separate processors. So there's not a need to have an ordering because they commute. So who cares what order they ran in?
I thought you were going to say something else about scaling, which is it also scales conceptually, right? You can wrap purses in lots of different kinds of contracts, right? So it scales in terms of reusability.
All right. If there aren't any more questions, I think, where are we on time?
Yeah, if there's no more questions, we should wrap it.
Yeah, let's wrap it up.
Last chance.
Well, we just test them.
Check, check, check. 1, 2, check.
Talk? Oh, yeah. Yeah, like this? Cool. I wish I had note cards for you. Just kidding.
I can throw candy at you.
Oh.
Termination semantics.
Cost models seem to, it didn't seem accurate anymore.
Okay.
Yeah.
You can, it's the pink card talk.
The what?
The pink card talk. You're terminated.
Should I?
Yeah, I think
should I go?
We're about
Yeah?
ready to rock.
All right.
Go ahead.
Hi, everyone. So I'll be talking today about termination semantics, the more popularly known as the cost model in documentation for RChain, but cost model is not really accurate, so I figured I'd take the opportunity to change some of the lingo. Yeah, so basically, as an overview, I am going to outline why we need termination semantics, or a model, such as the gas model for Ethereum, an analogous model for RChain, why that's necessary, what problem it solves, and kind of what Ethereum tapped into when they came up with their model. Explain that, and then go over what's specific to RChain, the problems that we face, and eventually some code. Okay, so the main issue is pretty simple. Basically that, if we don't charge people to run programs, then you can DOS a miner. You can deploy a program, since Rollin is Turing complete, that reduces infinitely. And obviously, we would like to avoid that. So in the same spirit as Ethereum, and really it's for any distributed system that offers like computation as a service, we want to charge the people that are using miner resources. What we're looking for is a framework to do that accurately, and one that allows us to preserve the concurrency semantics of the language. We can say that the termination model consists mainly of two parts, or I like to think of it as having two sections. The first part involves making termination proofs. And I know it looks like a lot, but it's really simple, and we'll go through it quick. But basically, the gas model, as Ethereum formulated it, was tapping into a method for generating termination proofs that has existed almost as long as the halting problem itself. So when Turing published his findings on the halting problem, essentially 13 years later, he introduced essentially this framework to say, or that allows you to convert a non-terminating program into a program that terminates. And we'd like to do this for Rollin. So yeah, take sigma to be a set of Rollin program states. W, a well-founded set. And just as a brief reminder, a well-founded set is just a set that has a least element, so a bottom. Eventually it bottoms out and there's no lower you can go. And then a set of operations. And the idea is to map the states of the program to elements of this set, right? And so even though my original program might continue infinitely, if I can map the states to a set that I know terminates, that I know has a bottom, then I can prove that my program also has a bottom. That's the general idea. So the first function, the termination argument search, we can think of that as a balance. Whatever we decide W to be, whether we decide for it to be, I don't know, the set of natural numbers, whether we decide for it to be tuples of natural numbers, or essentially any well-founded set that we like, we can think of the argument search as a balance. It says, at given program state, I have this much of W left, right? So if this is essentially like, for example, to stick with a lingo that we all know, on the EVM, if this is my program state, then this is a function that says, okay, given a program state, this is my remaining gas balance, right? Nothing so far that, sorry, let me check. Is that clear? More or less? Yeah. If anybody has any questions, feel free to holler.
How do gas happen minor back here?
Say again?
This mic.
Oh, cool.
You use the W well-founded set as saying it's a gas. Why is that?
Oh, because, yeah, essentially, good question. Yeah, gas is, or the set of natural numbers is a well-founded set, right? So all non-negative, integers, right? So if I have a balance and then I decrement, right, all the way down, right, then eventually I'm going to hit 0. Okay, so that's what they chose to represent this kind of descending relation, right? But my point is that it doesn't necessarily have to just be, just a counter, right? Does that kind of make more sense?
I guess I'll see.
He's setting it up so that we can talk. We got a mic. So he's setting it up so that he can talk about phlogiston, which it's a 4-component thing, right? So because the Ethereum model is gas is a number, right? And in RChain the phlogiston is a 4-component thing because we're trying to measure across different resources.
Right.
And so he's saying, well, look, there was actually Turing thought about this a long time ago. You just make it some abstract, well-founded set, right? It doesn't have to be just a number.
Right. So I'm saying our measure can vary, right? And in fact, well-founded sets in general, they are valid for induction. So, and that's what Turing realized essentially. Is like eventually I know I'm going to reach a bottom. So if I can prove that a certain predicate being true for now implies that it's true for the next value of my counter, then I know that it's true for all values of the set. But anyway, we should probably move on. So the validity check, yeah. That's number 2. Essentially, that says that, that the balance that we talked about earlier is decreasing. It says that if P and P prime are states, right, and we have a transition from the state P to the next state P prime, right, and that the balance of this program state P is greater than the minimum of whatever we choose for W to be, right? If this is true, and that implies that the value decreases, our balance decreases, then we know that the balance decreases across the entire evaluation, right? So as long as it's decreasing and as long as we have a bottom, we know that we have an endpoint. And that essentially provides a termination proof. Oh, and yeah, this is the point that oh, sorry, yeah.
why isn't that second condition that 5p greater than or equal to min of w automatically true because it's mapping into w, and how could you be below the bottom?
You don't have to have a continuous function.
Okay.
It could bounce. It could bounce all over, right?
Okay.
Right.
Cool. All right. Yeah. So the third function, which Turing did not include in his original publication, was that of a cost model. Hence my desire to change the lingo up a bit. A cost model in general is just a mapping from operations to a cost for that operation, right? You say, okay, so if omega is a set of operations that I can perform, right, and we're not committing to what those are going to be yet, right? If you give me an operation, I'll tell you how much it costs, okay? And what that does is it allows us to tune this check. If I can say that I know I perform this operation, and so I change from state p to p prime, then I can decrease my p-value by the cost of that one, right? And just to stick with the lingo we know, on the EVM, if you perform an operation, you decrease your gas balance by the cost of the operation. My point being, this is a much more general picture, and we have freedom to play with it. Yeah, so to recap, this gives us an endpoint. This tells us that we're approaching the endpoint, and this allows us to affect the speed at which we approach the endpoint. Yeah, and so essentially, like Ethereum understands very well, the idea is that we can leverage economics to disincentivize bad behavior in a decentralized setting, right? So if this is a termination proof part of gas, we also need an economic proof. And the reason we need this is because even if we can, force a program to terminate, a Rollin program that runs for 1 billion years is only marginally better than one that runs infinitely. So we want to disincentivize people from deploying even long-running computations, right? And so we'll be able to unify these concepts essentially by having the deployer pay to get the initial balance, right? Stuff we already know. So this part is all similar, right? Greg mentioned that flow does become, that's our analogous term for gas, is phlogiston flow. I mentioned that it was a 4-tuple. I'll expound on that a little bit later. For now, we're treating it as a 1-tuple that only quantifies compute complexity, not any sort of other spatial complexity, network access, anything like that. So right now, it's just the operations you perform. Cool? All right. Yeah, OK, so this stuff should all be familiar, too. Basically, when you deploy a program, you specify a pH limit. Here, we've chosen pH to be, or flow to be from the set of natural numbers. Conversion rate, and then this, essentially, since pH lim is a natural number and our conversion rate is in rev to natural numbers, then when we multiply the two, we get the amount of rev that you're going to have to take, that's going to have to be taken out of your wallet to pay for this computation, right? So once you've purchased the flow, then you get to set your initial balance and then proceed with the termination proof as in the last slide, okay? So far, all the same stuff that we're familiar with. Yeah, so I guess to recap on that, I just wanted to point out that we have freedom to play with the model. For example, if we choose our set to be the set of Rollin terms and our order to be this a subterm relationship, then as long as the program that you give me is decreasing in size, right, as it reduces, then I can prove that it terminates, right? So that's, as an example, that we have freedom to play kind of with the set. Of course, that's not true with Rollin in particular because we allow replication. And that's what we're going to talk about next. OK, so as opposed to the EVM, where essentially the cost of bytecode is specified and state changes are specified at that level, Rollin has a very tractable model that's, at least I would say, is fairly apparent in the code. Right? We have, it's pretty obvious, or you can see and reason through the semantics of the language, tie that to the model that we are given, which is RoCalc, and then kind of estimate how the messages in your program are going to flow. Right? And I think it's desirable for programmers to be able to tell how much their program is going to cost, or at least get an idea of how much certain portions of their program is going to cost just by looking at the source code. So we don't need to specify the cost of operations in terms of bytecodes or opcodes. We specify it in terms of the language constructs, which the model allows us to do. Right. So how do we build the checks that I first brought up into the evaluation of a program? And how does that affect the evaluation of the program? Because we're concurrent, right? So if I have to alter my program originally to deduct a counter, right, then by nature of providing the proof, right, I've altered how my program is going to run. So we want to minimize that as much as possible. So we get 3 flow-specific evaluation rules. And I think they at least kind of complement the original inference rules of the row calculus in some way. But the first one essentially says, right, that if I have a flow balance associated with a process, and that process is a par, then I can give both components of the par replicas of the initial flow balance. So in this case, and if anybody's unclear as to how we got to that point, feel free to speak up now.
Well, if you were duplicating the money, that would be bad. But
yes.
We'll see in the next rule, I think, that you can think of pH as more like a pointer to a wallet, because when you decrement it, all of them get decremented.
Yes, yeah, in spirit, yeah, no, good point. That's helpful. So not quite a wallet, right, because we don't want all decrements from a flow balance to have to be verified as transactions, because that would be abysmally slow. But you are correct. We can think of the flow balance here as a shared global counter. And that's what the second rule addresses. So we have that if we have an expression P that has a flow balance, right, and that term can reduce to P prime, altering its flow balance, because we have to deduct for the operation that we performed, and pH prime is greater than 0, then I can do this modification to flow concurrently. And I can have that modification witnessed by the other processes that have a replica, just as Mike said, right? So pretty straightforward. Good? Cool. And then finally, to enforce our invariant, we have that if P can reduce to another expression, and it tries to yield a negative flow balance, then it just becomes nil. So we cut the legs out from under the process, and we don't deduct the flow. And your computation's over.
And that is a point of some contention still, because we're considering allowing you to add more flow after the fact. But
yeah,
this is a pretty good initial proposal.
Yeah. Yeah. Go ahead.
Do you go through the concurrent execution if P and Q both reduce?
Do I show examples?
Yeah.
Yeah.
Okay, good.
Yeah. Oh, thank God. Yes. I come prepared. OK, let's start with arithmetic. Always a good demonstrative example. Yeah, so the deploy function at the top is the same one as was defined essentially in Michael Birch's paper, or sorry, presentation, at least in spirit anyway. We have, you'll have to trust that I know what the fields are, but we have a bunch of extra fields that I allotted for space. And the program, 1 + 1, par, 1 + 1, and then an initial flow balance, just to start simple, okay? When we call the deploy function, just as it was defined in the last presentation, we take the program and we par it with the current blockchain state, which is S, okay? In doing so, we associate the initial flow to the top level process. And by our rule that I showed in the last slide, we can say essentially now that if I have a flow paired with a top-level par, then I can distribute that. Okay? So now both of these processes can reduce concurrently. So let's say that our process on the left, not quite reduce, but is evaluated first. 1 + 1 is 2. Cool. All right? Let's say that it cost 1 flow to add things together. All right? So flow is decremented globally. Pretty simple so far. Let's say that the write process is evaluated next. That's going to take it down to 1. Ending up, the final process of 2, which is effectively nil, because we don't do anything with that 2. Is everyone clear on that? Because it's kind of foundational. Yeah? Pretty simple? Cool.
Because addition is commutative, if they'd gone the other way.
Right, yeah. And we'll see, like, with essentially how I'm building the cost model, we want to build the counter to be commutative. So we want, in any case, I mean, you know, addition and subtraction are commutative, but we want to maintain that modifications to the counter, or that the counter is eventually consistent. But I guess we can talk implementation after, if you want. So, right, so let's say that I added another 1 + 1, right? So I need 3 flow, I only have 2. We're going to go through the same song and dance, evaluating left to right. As we see, we're distributing across 3 processes now. Left evaluates, middle evaluates. That takes us down to 1, but 1 + 1 has yet to evaluate. Okay? So when we try to do that, we are going to yield, or we're going to try to yield, a -1 flow balance. And that's really bad. You're not allowed to do that. So we're just going to take the entire computation and squish it to nil. You don't get any of your effects. Flow stays the same, and all the rev that you attach to the contract is forfeited to the miner.
You know, if you call it out of flow status, then it would be oops.
Yeah. I did, yeah. Oopsie, yeah, right? Oops. Yeah. All right, that's a laugh. Okay. All right. So to describe more complex processes, we're going to need, although I understand the intent, and it is very simple to say that all of the RChain blockchain is, the entire state is a giant Rollin term, there is another component, which is the tuple space, and you can treat these as separate entities. And so to kind of get a better idea of how we interact in the store and how flow kind of impacts execution or evaluation, we're going to introduce a small tuple space grammar, just so we can describe, you know, how storage kind of looks as we're evaluating. So T, tuple space, is mapping from channels to data sets. Channels to a list of data. Your data can be a message, a persistent message, a read with a continuation, and a persistent read. And in the store, we keep flow balances with those. Clear? Cool. Yes? Question from the guy who's writing the storage.
I just wanted to, for people who are somewhat familiar with the way that RSpace looks right now, I just wanted to map those 4 things onto current. So
yeah.
The first one would be a produce with the persist flag set to false. The second one would be a produced with the persist flag set to true and some caveats. Then we have a consume, persist false, consume, persist true with some caveats.
Thank you. Great. Okay.
Oh, one other thing is you've simplified the consumes to be only on a single channel, and that's fine for the
presentation, but it's not accurate.
Yes, that's correct. OK. So let's say we want to deploy A. Let's say Alice wants to deploy A. Alice is going to call the deploy function on her program, which is going to par it with the state of the blockchain. It's going to be given some amount of flow debited from Alice's account. And let's say that the first term to execute, or sorry, oh no, right. OK, so we see our tuple space, yeah. We see our tuple space at data feed, right? So that's a quote, that's a channel, is currently empty. It's kind of like an idealized tuple space where nothing else, no other activity has happened over at data feed. We know that we can distribute flow. And let's say that the persistent send executes first. When the send executes, it's going to place at data and a modified flow amount at data feed, right? So what we have here is essentially that data was quoted, turned into a message, stored, and because we sent, we have to decrement flow by some amount. So that's why it goes from pH to pH prime. And we notice that the input has also witnessed the decrement. And the reason, and keep in mind, and I'll kind of demonstrate this later in other examples, but keep in mind that the reason that these flow counters are the same is because these two terms were deployed together. You use deployment to scope who pays for the program. If it's deployed together, then it assumes that all computation that occurs as a result of the deployment is paid for by the deployer, with a caveat, but we'll talk about that later. OK, so send executed. The receive is next to execute. So since send is persistent, it's effectively equal to send, we have x bang bang q equal to x bang q par, a bunch more of those, another x bang q. Can everyone see that? Yes. All right. So we have to treat the evaluation of x double bang q, at least to be accurate from a language perspective and to be accurate from the intended semantics of the language, as if it is a replicated send, right? And there are issues kind of with this that we have to address, which is like that doesn't terminate. That just keeps going forever. If you put x bang bang q to the blockchain, then ideally it stays there forever. So we have to find a way to kind of ameliorate the situation. We have to find a way to reconcile persistence and with efficiency and with finding someone to pay for it, essentially. So since the send is persistent, when the input executes, okay, it's going to take the message. It's going to take the message out. That's going to take this counter, pH prime, down to pH double prime. Since the message has been taken out, it has to be put back in. That's going to take the counter from pH double prime to pH triple prime. So what we saw is that when we have something stored, the send in the tuple space, right, you have to pay for every additional send that you put, or every additional time that you put the data back into the store. That's my interpretation. But
so this is a precursor to a rent model.
Well, no. Actually, no. Because in this case, thanks. Good question. It's leading. So in this case, we're still talking. We're still paying for operational complexity. This is just time complexity, right? We're paying for the action of sending, the action of receiving, the action of sending again. Okay. What Greg's talking about is later I'll introduce somewhat informally the concept of rent, which is a persistent payment. Okay. So after the message is read, it's substituted into the body, which we can turn around and C, we had drop Z there, so Z is substituted for at data. So we get drop at data, and now we're going to have to perform the drop, converting the process in the top to just plain old data. And that costs 1 as well, so we have the quadruple pH. And that is going to be our resting state. So that's the final pH value. That's one evaluation. So is everyone pretty much clear on that? Any questions? I'd be happy to pause to take some. All right, cool. So as I said, deployment scopes your payment plan, right? So let's assume that you have, instead of just Alice deploying A and paying for everything, the entire complement inside of the program, let's say that you have 2 different entities defining P and Q. We can think of P as a process that was created to persist data to a data feed, right? But we don't always want the person or the entity consuming the data to pay for the continuation. We want to be able to separate the payer from the sender. And so we do this by deploying them separately. Since they're deployed concurrently, they're handed 2 different counters, PHP, PHQ. Now, all the costs that were shared in the last evaluation are going to be accumulated in their respective repositories, in their respective balances. So what Q doesn't affect the balance of P. What P doesn't affect the balance of Q. And what we should see, if we're witnessing the same behavior, right, and the same costs are still achieved at the end of the program, is the same amount of ticks, right? We're still executing the same actions. They're just based in different kind of repos. And we see that to be true. So we see that PHP has 2 tick marks, so it's executed at least 2 actions, and that Q also has 2 tick marks, giving a total of 4, which is the same as the last evaluation. So contracts. Yes?
Can I get you to go back to that?
Sure.
Yeah? Okay. There. So the P double prime on both of the 2 different entities that we'd instantiated and then sent some stuff to. So I'm thinking that if these were in different namespaces, because it's a transaction that's crossing over or something, and based on some of the operational complexity economics, if there was a different cost of performing the same action in these different namespaces, that would not invalidate this logic, because the prime on PH double prime in Q can represent the operational complexity cost of Q. And the other one will keep it in its own, and then it'll come back and tell you how much the whole thing costs. Is that right? Or no?
That's the thinking.
Okay.
It's it's important, and the constraint that we have to enforce is that within a given validator set, that they're using the same measure, right? Because we have to be able to validate that, like when I run a program, when validators validate my program, no matter what execution order they go through, right? Or no matter what execution order the program goes through, since we reach consensus on COM events, if we have the same execution, if we reach consensus on a particular pathway, then we should arrive at the same flow balance, right? So even though the language is non-deterministic, we have determinism in the end result of the flow balance. So if,
So so the measure is a parameter of the namespace, is that what you're saying?
Yes, ideally, yeah.
And how do you set that? Like, when does that get set? Because a lot of namespaces aren't going to be populated when the network is initialized.
That would it would have to be set when the namespace is created.
They're all created at the very beginning. Well, the regions are created, right? And the namespaces then have to exist. Everybody has to know at the very beginning what the measure is.
Yeah, it's the region that's going to come, the specification of the region has to come with the measure, right?
So if you have two regions with different measures,
Still
and you want to combine them into a single namespace.
When you go up into the join, right?
So there's something to work out there, right? Is how you combine two measures
How
that
you
might not be
combine
compatible into a new one.
Yeah, exactly.
Absolutely.
So you either take the min or the max or some
Yeah.
combination. Exactly.
Okay.
One reasonable way to do it would be that the cost of running in A join B is the cost of running in A plus the cost of running in B.
Yeah.
Another difference between the regions is going to be the extra off-chain stuff that they provide access to. And those can be, those off-chain resources can have their own phlogiston costs for accessing. So if you're doing off-chain storage as a service, that can be exposed as having some phlogiston cost.
Well, my opinion on that is that it has to be standardized in the language. Essentially, like because we're basing the payment semantics on like the specification of the language itself, and we want the right. We essentially want it to be defined for the entire language if it is defined at all. Right. So if you've written kind of a library, right, that I suppose like includes functions for accessing storage, off-chain storage, then yes, that's fine as long as it's part of the language distribution, right? Does that make sense?
The stuff that's written in Rollin, sure.
Yeah.
Anything that happens off-chain, there's nothing in the interpreter that knows about how it is, and so the region just declares by fiat, this is what it costs if you want to use this.
So, for example, if the region offers a SAT solver, right, then it just declares this is how much it costs to run SAT solver.
Right. So, is everybody good? Cool. Contracts. So in the last presentation, Kyle mentioned that fors and contracts were, there's a slight semantic difference between them. And the semantic difference arises at the level of payment. Normally, these would be the same. These would be just like different ways to specify the same thing. But we're using contract instead as an expression of intent to not pay for something. And this is useful because it's, in a lot of cases, it's useful to be able to separate or to be able to choose when the sender pays, right? So the entity causing the continuation to execute pays for the continuation, right? In line with causality. You sent the message, so you should pay for the result. And of being able to separate the sender from the receiver, as in the example of the data feed that I gave before. So we want both options. And the way you can think about it is that when use call syntax, you link at runtime whatever flow counter is attached to the call to the continuation of the contract, right? And think about if we didn't do this. Think about if the persisted for were the same as a contract and that you deployed the contract. What would that mean? That would mean that every time your contract is invoked, you have to pay for it, which is suboptimal for public processes. So we give an option. So I have an example of what that difference would look like. If we have Alice and Bob, Alice is deploying a contract, Bob is deploying a for, a persisted for. They deploy concurrently, get their respective flow balances. Alice's flow, Bob's flow. This idealized tuple space with the channel X is empty, no activity so far. First, let's say that Bob's persistent for is put into the tuple space, right? So he's going to store permanently z.p. That's going to say, if you send something here and it matches z, right, then execute p with z substituted for the message that I get. Noticing that Bob's flow is decremented by the cost of the receive, which we're saying is prime. Next, let's say that Alice's contract deployment executes. Okay, so it's put up to the blockchain. We can think of this as the initial read being the same as a persistent read, right? You read from the channel X, and then you store the continuation there. But when the contract's put into the tuple space, it's not given a flow counter. So if you tried to invoke it without giving it flow, well, you wouldn't. But if you could try to invoke it without giving it flow, it wouldn't execute. So essentially, contract waits there until it's given flow to execute. And probably a good point to mention is that if you try to use send syntax to invoke a contract, it's not going to reduce. If you try to use call syntax to invoke a persisted for, it's not going to reduce. So the syntax constructs have to be dual, right? We don't evaluate anything else. So it was something to mention. OK, cool. So this is the last slide. Now let's say that in parallel with the persisted for in the contract that I just deployed, let's say that we have two entities trying to invoke these, right? Let's say that we have Carol and Dansworth trying to, I don't know if that's a name. And Dansworth is trying to invoke the persisted for by sending it a message, and Carol is trying to call the contract. So these are only going to meet with their respective duals. Carol's flow is going to be linked to the contract. Dansworth's is not to the persistent read. So what we see here is that the original flow, the persistent for was given, is used to fund the continuation, right, BB. And that C is threaded through the receive and the send to the continuation. And then, oh, and of course, since they're both persistent, they both stay on chain. And the modifications to flow of B were recognized for the persistent read, but since contract doesn't store any flow, it's just stored with kind of like a null reference. So that's the end of operational phlogiston. It gives a very kind of like a very natural, at least I think, flow as to easy to determine from the source code where your money's going to go and who's paying for what, which was the intent on the outset. Now, the end. Question?
You were going to get to storage.
That's right. OK, cool. Let's get to storage. Do I have a marker? OK, so because Rolling's an asynchronous language, we can never really know when a program has reduced entirely, at least without like runtime reflective checks, right? To be able to determine entirely that, if I've stored a read in the tuple space, that no write will ever come along and invoke that continuation. It's just not something we can know. So there's the potential for messages and reads to hang out in storage forever, right? We can't just say that, oh, because you haven't gotten a response for some arbitrary amount of time, we are going to reduce, we're going to take your thing out of the tuple space. At least that would seem to be an arbitrary measure. So given persistence.
No, we have a hook for that. OK, you're live.
Sorry. So we need a way to reconcile persistence with compensating miners for their resources. And to this end, we've introduced another component to Flow. And this is a fast follow from Mercury. For sure, building the model to cover operational costs. And if it's not included in the Mercury release, it'll be a fast follow. The idea is, at least this is my idea for it, is that since processes proceed and they get operational flow, that entities that persist things to the tuple space should get their own form of flow. And those would be channels. So processes get operational flow, channels get storage flow, right? And we want to create a framework where you can time activity on a channel, essentially a pay-to-play access to the channel. So we can say that if you were given 10 storage flow and 10 storage flow buys, 20 days of reads and writes, that the channel stays open for 20 days. At the end of those 20 days, we have a choice. We can say either, unequivocally, we're going to remove everything from the channel since your flow ran out, or we can try to offer a way to refill that flow, because we have processes that need to maintain an internal state. For example, now, no one's ever going to read from X, but if we introduce this idea of storage flow and we say that, okay, when you introduce a channel, right, the entity associated with creating that channel is going to have to provide some means to pay for access to the channel, okay? So this is Alice's channel. We put it into the tuple space, and inside of this, inside the scope of the channel, we deploy a contract. And every time the contract's invoked, and I suppose actually now that I look at it, it's never going to be invoked, but no, that's not true. No, because foo's not limited to, scope. So it could be invoked. If we say that Alice gets 20 days to run this channel, and that over those 20 days, we'll, process whatever you want, right? We'll do all these sends for every invocation of the contract. And at the end of the 20 days, we say, okay, time's up, we're stripping the channel. It precludes contracts from maintaining an internal state. So it seems to be that if we introduce a method to pay for persisted storage, then we also have to provide with it a method for refilling flow to pay for persisted storage. So that's kind of the motivation and the idea. How does this fit with the definitions that we gave in the first slide? With our validity check and our argument check, and with our cost model.
Joe, are you going to, because obviously storage isn't just time, right? Storage is total amount
spatial,
of data.
Right?
Yeah.
Definitely.
Okay, so are you going to touch on that, or?
Sure. No, that's good. Yeah. Okay. If you were wondering, other people were too. So yes, storage by nature needs to be a spatiotemporal cost, right? We need to have one that. Yeah, I said that right. Okay. We need to have one that periodically we're charged for maintaining access to the channel, for processing or for keeping the channel open, so that you can't just throw a channel up once and have it stay there forever. We also need to include a spatial cost, which is how much
storage is left available, and how much do you want to charge for storage, right? So if you have a cost, a spatial cost, that you pay once, 10 minutes, cool, and then periodically after that, pay a time cost is how I imagine it going. So, cool. How does that fit with our initial definition of state and of our descending condition on flow, right? Well, like we did with introducing the tuple space grammar during the evaluation, let's just amend our definition of state. So a product of a Rollin term and a tuple space we can think of as a state, right? And we want to say that essentially every time that I have P and T moving to P prime, T prime, where they're not necessarily different from P or T, but either one could be, that we also have that the measure for P, where we have a pair of conditions, that the balance or operational balance for P is greater than operational balance for P prime. So we'll do an O here to denote operational. And that the spatial flow for P is greater than spatial flow for P prime. Or sorry, here we have it. Yeah, for T is greater than that for T prime. Cool. So basically, shorthand for saying that if your process performs an operation and that takes it to P prime, then P prime has to have less flow than P did. And if it performs an operation that affects the tuple space, say, for example, adding a channel or updating a channel, that the flow allocated for storage must also be decreased. So just by kind of like amending it and turning it into a product and reformulating our evaluation rules, we can include storage flow, or at least the idea of it, in our evaluation semantics.
So this proposal has channels tied to wallets that are funding them, or flow packages that are funding them. But it seems possible that multiple different parties could deploy contracts that are all listening on the same name. That may be desirable in some circumstance. But then funding those that some contracts may run out of money before other ones, that they may want to continue funding them.
Which is that in the case, for example, that someone else was deploying the @foo contract at the exact same time, and that @foo had never been created before, we don't know which wallet is going to be associated with the channel when it's put into the store. So we don't know who's supposed to pay for it. And kind of an open issue in kind of deciding this is, what's the correct approach? Would it just be first come, first serves? First come, first serve? That would be an easy solution, but it also kind of defeats the purpose of making it easy to reason about the cost of your program. So that is an open question and something we're going to address in the breakouts this afternoon. Anything else? I know I've been going on for a while, but.
So how is the reduction context marking in the presentation of term calculi connected with this method?
Do you mean in, huh? Oh, okay. Are you talking about term hole context? Yeah. I hadn't considered term context in this setting, but it's not a bad idea. I would compare it to a process environment, which is a mapping essentially normally from names to channels, right? But we do it with De Bruijn indices, so it's actually mapping from integers to pars. But basically, the channels available to a process describe its environment in a similar way that the context of a process describes the channels and interactions available to it. So what I would say is just naturally, if we can attach costs to environmental changes, then there would be a translation into contextual changes. Does that make sense? We would be able to attach, it seems like we'd be able to attach some analogous cost to term context, right? And you bring up a good point, actually, which is that this would be like a really cool thing to investigate as just kind of a general, as a general exploration of row calculus, right? If you can attach semantics to like a, like a term calculus and decide under which conditions it's growing or shrinking based on substitutions and reductions, and you can essentially get like a good idea for how rewrite systems, or you can prove termination for rewrite systems, which has been done before. And I think someone should do it for row calculus. I don't know who that'll be. 5 minutes. Any other questions? Cool. You guys have been great. Thanks. Should I turn this off? Should I turn this off?
Test.